Ladies and gentlemen, I would like to welcome you to our presentation of ATENA software and Cervenka Consulting on nonlinear analysis and how it can be used in design and assessment of reinforced concrete structures. Well, this slide kind of summarizes some of the typical applications, bridge construction, hydration, heat development, and checking of massive concrete structures. So why do we want to talk about nonlinear analysis? That's because this is our bread and butter. We are developing software and technologies for advanced modeling and simulation of reinforced concrete structures. As you can see, some slides of the software for the application of bridges, but of course it can be used also for other structures. In my talk, I would like to give first some idea about motivation, then how we put it into some safety framework, and how we evaluate model uncertainty on, and this I would like to demonstrate on some blind competitions. And then I will conclude with two examples coming from bridges. So the motivation, we all know that when we develop models and formulas, we use laboratory experiments. The laboratory experiments are relatively simple, typically beams, prisms, slabs, also or walls with simple geometries, also small sizes. But in practice, we often analyzing something big, something complicated, like you can see here, these pieces of steel embedded into massive concrete slab, or we have some complicated architectural shapes, or nowadays we have this technology of 3D printing, which also is quite different from our assumptions that were used in developing our standard formulas. So that's when nonlinear analysis is an can be used with advantage to check our design. So it is typically not a tool to directly dimension your structure or find a reinforcement, but it is an ideal tool to check the structure, like this example I'm showing now of a seismic wall. This is a laboratory experiment because we can then compare, as you can see at the bottom here, quite a good prediction. This is the famous CAMOS benchmark from France. And our ATENA model shows very nice the crack development, opening and closing of cracks, the crushing of the concrete in this bottom right corner. There's here something more complicated, which you may encounter in practice. So 18-story building, again modeled in ATENA for some accelerogram based on existing seismic action. But of course we can analyze other structures also. Another model here I want to show on the top right is the failure modeling and calculation of the ultimate load carrying capacity of a pre-stressed concrete, reinforced concrete girder, precast girder failing in shear. And I mentioned this technology of 3D printing. So of course we can model that with ATENA software as well to take into account the printing process. The objective of this is mainly to check whether the structure doesn't collapse during the printing, or sometimes the printing process is also important to consider for the evaluation of the final behavior of the structure or the final strength of the structure. Well, of course, in practice, we need to put this when assessing structures in practice or designing structures in practice, we need to put everything into some safety formats. So very quickly, there are formats available. FIB model code is one of the best sources. In Eurocode, now the new version will also include safety formats for nonlinear analysis. And they all can be quite nicely transferred also, I think, into the ACI concept, where this resistance factor is typically including the model uncertainty and the material uncertainty and geometric uncertainty. So with this process, one can always load the structure up to failure and use this resistance factor calculated from the model uncertainty, material and geometric uncertainty to come up with the design strength of your structure. So this graph gives you also the main difference between the standard approach, because with nonlinear analysis we are always loading the structure, or the best way how to assess the structure is to load it up to failure and then compare the obtained load with the design load, considering some safety factors. Now about the model uncertainty. Well, for ATENA software, we calculated that. We evaluated the value to be about 1.2. And the best way how to check the model uncertainty is to look at or participate in some blind competitions. So I will show this one, which to give as an idea how such competitions works. So typically there is an experiment, typically at some university. This one was in 2015 organized by Professor Collins at the Toronto University. Here you see the publication where the results have been published at Concrete International, volume 37. And you see quite large beam. Here you see the model in ATENA and how the crack pattern very well compares with the experiment, and also the calculated peak loads were quite good match. Actually, ATENA was the winner in this competition. So this competition in this beam actually first failed on the right side, where there were no stirrups, no stirrup reinforcement, and then they put some ties to strengthen it, continue with load until the failure occurred also on the left side. This slide shows gives the summary of our participation in some blind competitions over many years. And you see these green points indicate our results. The gray bars provide the information about the scatter observed in those blind competitions. So the scatter was quite big. So we can see it's always not easy to predict these results or these tests, which are typically slabs, beams, or columns. So we are happy that we are usually quite consistent and have quite good and high reliability of the simulation by our software. And these results, I want to point out, are not only from our team. Sometimes our users using ATENA software obtain the best predictions. Now I would like to conclude with some examples how it can be used in practice. I'll show two bridges. First bridge is a pre-stressed bridge by segmental balance cantilever construction. Here you see the individual segments. We simulated this section of the bridge to capture some cracking which were observed. So very detailed model was created, or is able to create within our software. Here you see the segments, you see the pre-stressing tendons, you see here the modeling of the reinforcement inside each segment. So very detailed of the model can be, of the reinforcement can be very effectively taken into account. Also the contacts between the segments. Actually, to give you an idea of the purpose of this analysis, that's because of these cracks which were observed, these kind of shear diagonal cracks. You see the photo of the bottom of the bridge were observed soon after the construction. So to explain the behavior, or to explain the behavior of the bridge and explain the presence, the reason for these cracks, The quite detailed construction process was taken into account, starting with the balance cantilever constructions, pre-stressing of the two spans. There was a large construction break due to some administrative problems. In this construction break, there was it was identified that some thermal events during this period, when the bridge was still not yet completed, caused the development of these cracks. It was very interesting to know that these cracks would not have been detected and have not been detected by the standard design using the beam approach, where the plane section is typically assumed to be plane. But this was not the case in this situation, especially with these thermal gradients and also the effect of the location of the pre-stressing tendons. So this is a big lesson learned from this analysis, that the standard beam approaches are not able to discover these problems which might happen in case the design is very optimized. So we also loaded the beam, the bridge, or the part of the bridge up to failure. Here you see this load displacement curve. Some critical points have been identified. This point corresponds to the onset of reinforcement yielding. The green point corresponds to the start of cables, yielding of cables. But the main critical point was this one with the white rectangle, where the crashing was reaching limiting strains. So this was identified as the critical point and as the failure load of the structure. But it was sufficiently above the design load level, so it was not a problem. Especially, however, the strengthening was necessary to reach this satisfactory behavior, and the strengthening was also modeled in ATENA software. Here we see the modeling by these internal or these external tendons inside the box girder. Another bridge I want to show is a reinforced concrete bridge. And why I'm showing it, because it is using very interesting and new durability corrosion model, which is available in our software. And the main aspects of this model are shown here. So we can model the bridge behavior in time. In this case, it was over 150 years. And let's talk about what we see on these figures. So this top left figure shows the chloride concentration at the depth of reinforcement. Below we see the corrosion levels of the reinforcement. Again, you can see how the software allows the modeling of each reinforcement, and also to take into account how it can be affected by the corrosion process. And you nicely see how these areas of highest corrosion are somehow identified by the presence of cracks. So the model takes into account the fact that the chlorides will propagate faster if there are cracks. So this is one of the unique features of the software that allows to take this into account. So that's what you see at this bottom right figure. You see the location of the cracks shown inside the structure. Of course, those are micro cracks, so we should understand that they may not be visible, some of them. And that's why we can also show the cracks not only as lines, but also as their most probable maximum thickness. So we see them in these colors at the top of the bridge and also at the bottom of the bridge. So this somehow highlights some of the unique features of ATENA software for modeling durability problems, corrosion-induced damage, and how we can use that information. So we can use it to calculate the strength of the structure. So these curves calculate the load carrying capacity of the bridge depending on time. So the green curve is the original strength of the bridge, original load carrying capacity of the bridge without any corrosion. And as the time goes and the corrosion takes place, we see the degradation of the structure. And we can then plot that in time, considering some of the safety formats. And we can see the evaluation of the design strength of the bridge in time. So we see how it degrades. And from this graph, we can then identify when the design strength reaches the ultimate limit state. We can identify the time when the bridge should be removed or maybe retrofitted. So with this, I would like to conclude and bring out our motto of our work, that is to test your structure before you build it. And we recommend to use ATENA to do that. You are welcome to go to our website, download a trial version, test it by yourself. And also, we would be very happy to welcome you at the exhibition hall at the booth number 700, where we would be happy to share with you the latest information and the latest development in our company and in our technology. Also, you can see us at LinkedIn, Facebook, Twitter, and YouTube. Especially YouTube is nowadays interesting because there are many tutorials and videos that can help you. So thank you for your attention and hope to see you at the exhibition hall. Goodbye.
ATENA program produced by Cervenka Company. You can find us via the website and download the program from it, or on YouTube by name Cervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.